Welcome to the Educational Forum. This program is brought to you by the Massachusetts School of Law at Andover. Here at the Massachusetts School of Law, we held a conference to discuss some of the issues facing our world in regards to global climate change. On this show, and the others to follow, we take you to the conference. I am Kurt Olson, and I will be your host for this program. To quote from Earth Under Fire, How Global Warming is Changing the World by Gary Brash, let me state the goal clearly. No policy should be promulgated, no program initiated, no alliance sealed, no machine designed or built, no land use permitted, no product introduced, no law passed, no politician elected, unless the action is a step forward to reduction and reversal of the effect of greenhouse gases. Brash published this book in 2007. Tragically, few governments have taken steps to meet this challenge. Among those that have, the United States is conspicuously absent. As many of the leaders of the movement to address this most monumental of challenges have said, action to address the issue will have to come from the bottom up because politicians remain blissfully unaware of the gargantuan challenge facing humankind. At this conference, we aim to inform the public about the nature and extent of the threat and hopefully to enable citizens, municipalities, states, and regions to take the actions that need to be taken to ensure that future generations will inherit a world in a marginally habitable state. The scientists on this panel will address some of these issues in greater depth. The first session of the conference was entitled, It's Just the Accepted Science. Our panelists are Dr. Cameron Wake, a research professor with the Institute for the Study of Earth, Oceans, and Space, and the Department of Earth Sciences at the University of New Hampshire. He directs an active research program investigating regional climate and environmental change through the analysis of ice cores and instrumental records. Additionally, as part of the Northeast Climate Impact Assessment, Dr. Wake co-led research detailing past and future climate changes in the U.S. Northeast.
All right, let me start by telling you what I'm going to tell you. Three things I want you to take home from what I say today. First of all, climate changes. Climate always has changed and climate always will change for a whole variety of reasons. What's new today is that humans are now a driver of that climate change. The second thing is that I see this as this whole issue of global warming, anthropogenic climate change, as a moral issue, and for two reasons. The first one is that all that carbon dioxide that we emitted as we drove here today is going to be in the atmosphere on average for about 100 years. And that really points to the fact that while our generation, my parents' generation has reaped all the benefits of cheap fossil fuel energy, most of the consequences are being put on our children and grandchildren and great-grandchildren. And that's a moral problem because we're giving them a huge problem that we've reaped all the benefits from. It's also a moral issue on the fact that it is those who are most vulnerable today who have the least capacity to adapt. And you really need look no further than all of those images we saw from New Orleans when Hurricane Katrina hit. It is the people who did not have the resources to leave, did not have the resources to protect their home, or they were in the hospital that suffered the most. And the same is going to be true with climate change. Some of us will be able to adapt. If you have resources, you'll be able to figure out what to do. But those people who don't have those resources are going to suffer the most. And then finally, the third point I want you to leave with today is that there is actually tremendous opportunity here to reduce our greenhouse gas emissions and solve four problems at once. We can address the global climate change issue. We can actually develop a whole new economy that's centered around green jobs, and I'll point to some specifics at the end of my talk today of what we're thinking about in the state of New Hampshire. So green jobs, the economy. We can deal with energy security. The more energy that we produce at home, the better off we're going to be. And then finally, there's a whole issue on sort of human health and air pollution that we can solve by reducing the toxics that we put in the atmosphere that are associated with greenhouse gas emissions. So that's sort of the frame, big picture. I'm going to try to talk for about 25 minutes, and Nancy will do the same, and then hopefully we'll have a robust discussion. All right, so I'm an ice core paleoclimatologist, so let's start with some ice core data. This is perhaps the second most famous environmental record on the surface of the Earth after the Mauna Loa carbon dioxide record. And what you're seeing here is a record from an ice core extending back 420,000 years. This is an ice core drilled in Antarctica, drilled by the Russians, analyzed by the French, and by the Americans. And we've got 3 records here. In black on the bottom, you see temperature changes over 420,000 years. Above that in the blue, you see changes in methane, which is a key greenhouse gas. Then above that in red, you see changes in carbon dioxide. In the black boxes, I've highlighted the areas that we call interglacial periods. What you see from this record, 2 main things really come out. One is that there are these cycles in Earth's climate that last about 100, 110,000 years, where it's cold, there's low methane and low carbon dioxide for 80 to 90 to 100,000 years, and then there's warmer temperatures, higher methane and higher carbon dioxide. There's this cycle of about 110,000 years that's gone back, so we've had 4 what we call glacial interglacial cycles over the course of the last 420,000 years. The second thing that's obvious from this plot is that there is an intricate link between carbon dioxide, methane, and temperature. More greenhouse gas, warmer temperatures, less greenhouse gas, cooler temperatures. Now, it's actually interesting because a lot of the naysayers for climate change will show this plot and say, well, we now know actually that temperature changes first and that changes greenhouse gases, so there's nothing to worry about. What's interesting actually is temperature does begin to change first because of the Earth's response to changes in orbital cycles that change the amount of energy that we get from the sun. But it turns out that half of the temperature change is actually driven by a positive feedback loop from an increase in greenhouse gases. We warm up the climate, we have more carbon dioxide that comes out of the ocean, we have wetter conditions, more wetlands, we have more methane, and that serves to warm the temperature. But you cannot sort of pull apart the fact that greenhouse gases play a critical role in the temperature of the planet. We also use this Vostok ice core record to put the current situation that we're in into perspective. So here's the carbon dioxide record that I just showed you from Vostok. You'll see that carbon dioxide, greatly expanded y-axis here. You'll see that carbon dioxide has not been above 300 parts per million for the last 420,000 years, right? It's ranged from 180 to 300 parts per million. The Earth's system has really contained carbon dioxide in that range because of a whole bunch of feedback loops between the biosphere, the terrestrial biosphere, the marine biosphere, the oceans. And along come humans. It's kind of a little tough. It's just off the edge of the screen over there. We started monitoring carbon dioxide in the atmosphere in 1957 in Mauna Loa. Charles Keeling started collecting those records. We have increased the CO2 content of the atmosphere to an extent that's similar that we see between a shift of a glacial and interglacial transition. And that is all the data we really need to show that humans are dramatically changing the Earth's climate system. Now, there's a great saying when I first came to New England 2 decades ago now that says, usually issued by parents to their wayward children, saying, if you're not careful, you're going to end up where you're going. And that's exactly what's going to happen with carbon dioxide in the atmosphere if we continue to rely upon fossil fuels as our main source of energy. Best estimates of about 1,000 parts per million by volume by the end of the century, if we continue to rely upon fossil fuels. And that is going to result in catastrophic climate change. And I'll talk to you a little bit about what I mean by catastrophic climate change. Conversely, if we follow a pathway where we pursue energy efficiency and we pursue clean energy, we might be able to stabilize the atmosphere at 400, 450 parts per million, at which time there will be climate change we have to deal with, but perhaps not catastrophic climate change. There was a very influential paper that came out this year written by James Hansen from the Goddard Institute of Space Studies, who is now basically indicating that what we need to stabilize our greenhouse gas, our carbon dioxide concentrations at 350 parts per million. His claim is that at 450 parts per million, we essentially melt Greenland and a significant portion of Antarctica, and sea levels go up by many meters, and that's something that we want to avoid. So right now, the scientific community actually isn't completely clear on exactly what our target should be, but we're pretty sure it's got to be less than 450 parts per million and might be lower than what levels are currently today. We can no longer sort of wait to solve this problem. We have no time. We've run out of time. We have to figure out how to solve this problem right away. And actually picking up on something that Kurt had said, we are now increasing greenhouse gases at a rate that is above sort of the worst case scenario that the Intergovernmental Panel on Climate Change said it would be, what, 2 years ago? And the issue here is that while Western nations, albeit not the United States, have decided to do something about this, China and India are growing at an incredible rate. And there's one thing I know for sure, is that China and India are not going to act unless the United States acts. We can't be sure that if we act, that they'll act, but we know that they will not act without us acting. Maybe that sounds a bit like Donald Rumsfeld, but it's really important that the United States has to take the lead on this issue because we have been traditionally the largest emitter of greenhouse gases. And plus, we have, I think, the technology and the wherewithal, and once we decide to solve this problem, that we will actually figure out how to solve it. And what better way to actually grow our economy in the future than selling all that technology to China and India. All right, a couple of other plots from the Intergovernmental Panel on Climate Change, just to show you it's not just a carbon dioxide story. This is a record going back 1,000 years. We're looking at methane, which is another powerful greenhouse gas in the atmosphere. You can see it's gone up dramatically in the last few decades. And then the same for nitrous oxide, also a very powerful greenhouse gas, also increasing. So we're really changing the content of the atmosphere. Why are greenhouse gases important? We're not going to go through all the physics of the greenhouse effect. It's pretty simple, though. As you know, it gets colder in New England as winter's approaching. What do? We put blankets on our beds. And greenhouse gases in the atmosphere are just like putting a blanket on the bed. It serves to trap the radiation coming from your body so you're warmer. It's exactly what greenhouse gases do in the atmosphere. More greenhouse gas, we trap more radiation coming from the Earth. The planet warms up in response. I'm going to move now from sort of really quite long records back to something that's a little bit more on a time frame that we can understand. And this is a paper that's just come out by Michael Mann. You might have heard of the hockey stick record. This is the new version of the hockey stick. And the real dramatic part of it is off the screen on the right-hand side. So what Michael Mann has done is talk to a whole bunch of paleoclimatologists like me and many others and assembled a composite record of temperature change in the northern hemisphere by piecing together ice core records and tree ring records and coral records and instrumental records to try and understand how our climate's changed, in this case, over the last 1,000 years. And what you see is that he's taking his two records, which are in yellow and green and black, and comparing them to many other authors who have done a similar effort, and you see that there's lots of sort of wiggles and variability, but you see some really strong patterns here. It was warmer in the northern hemisphere back in the early part of the millennium. It was colder during this period called the Little Ice Age. But you can see as we get up to this Anthropocene era, this era where human beings are really changing climate, you see this dramatic increase in the temperature of the surface of the Earth. It's now warmer than it's been for the last 1,000 years, and we actually know why it's been warmer, and I'll talk about that. So here's some plots right from the Intergovernmental Panel on Climate Change. Global average temperature, that top one's hard to see. Global average sea level in the middle, and northern hemisphere snow cover. So you can see that our temperatures are continuing to rise. We're seeing sea levels around the globe rise, and we're seeing our northern hemisphere snow cover decrease substantially. So how do we know that actually humans are causing this climate change? Well, the central effort of the Intergovernmental Panel on Climate Change is to try and identify this fingerprint of human activity on the climate system. And the way we do this is, first of all, we now have a good idea of how Earth's climate has changed in the past. And over the course of the past 20 years, there have been many what we call global circulation models, mathematical models of the Earth's climate system that have been developed that do a good job at recreating the Earth's climate. They're models. They're not perfect, but they're pretty good at recreating Earth's climate. And what we do with these models is we actually force them with different processes. So why does climate change? It changes because the output from the sun changes. It changes because we have volcanic eruptions. It changes because we put greenhouse gases in the atmosphere. It changes because we put sulfate aerosols in the atmosphere which cool it. So there's lots of competing processes. And what we do is actually look at how climate has changed in the past, and that's actually the black line here. That's that graph I just showed you in the previous plot. That's how climate has changed. And then what we do is we take what we know about how these forcings have changed, in this case over the last 100 years, primarily from solar variability and volcanic eruptions, and we model how we think, we put these into the models, and the output from the model is how the temperature of the planet has changed. And this sort of god-awful yellow stuff here is the outputs from literally hundreds of different model runs running on sort of 15 or 18 different GCMs from groups around the world. This is not one group, this is many different groups providing this. And what you see is that when we force this with volcanic eruptions and solar variability, and in this case, all the greenhouse gases we've put into the atmosphere, as well as the sulfate aerosol we've put in the atmosphere, you can see that the models capture the warming over the course of the last 3 to 4 decades relatively well. They're not perfect, but they capture that warming. Now, if you do the same exercise and you don't include the anthropogenic forcing, so here we're just including volcanoes and solar variability, you see we don't capture that warming. You cannot explain the warming over the course of the past 3 to 4 decades by natural variability in the climate system. It's not about sort of natural versus anthropogenic. It's all happening, except we know for this period it's driven primarily by anthropogenic causes, which is us putting greenhouse gas in the atmosphere. That is the fingerprint of human-derived climate change. And it's very clear now. We've now done this for the last decade. Lots of different models, lots of different modelers, and the answer is still the same. We know that humans are the cause of the warming that we've seen over the last 3 to 4 decades. There's no doubt in the scientific community of that. We are causing climate to change. So we know that from looking just at carbon dioxide levels in the atmosphere and comparing them to paleoclimate records, and we know that from this sophisticated computer modeling exercise that we've now been doing for the last 10 to 15 years. What the IPCC has done is actually taken this a step farther, and they've looked at sort of all different regions. So you can do the same exercise for North America, or Africa, or Asia, or Australia. You can look just at the global oceans, just at global land. You can look at them all together. You get the same response from all of them. That's really this fingerprint of global climate change that the Intergovernmental Panel on Climate Change has come to. There's a few responses in the Earth system that scientists have been, dare I say, shocked over the course of the past 1 to 2 years, which illustrates to us that the Earth system is actually changing far more rapidly than any scientist predicted 5 years ago. So in fact, all of the estimates I know of are either reasonable or the Earth the Earth system is actually responding more rapidly than scientists suspected. In no circumstances do I know of any of the projections that were issued 5 years ago where the Earth system is responding slower. And I want to talk about 2 of these. The first one is Arctic sea ice. So this is Arctic sea ice in the Arctic Ocean, North America here, Russia over here. And the purples indicate 100% sea ice, and the red sort of 90% sea ice. So this is sea ice on September 21st in 1980, as viewed from satellite information. So this is really solid data. Now, if we look at what the sea ice was last year on September 22nd, 2007, you can see that we're missing this huge chunk of sea ice in the Arctic Ocean above Alaska and Siberia. All right? No scientist 5 years ago predicted this. And what's happening is that we've seen warming in the Arctic, we've seen a gradual decline in Arctic sea ice, but we've essentially seen the loss of what we call multi-year sea ice, which is on the order of sort of 15 to 20 feet thick. So as that sea ice has disappeared, the Arctic has become much more vulnerable to a warm summer, and that's what happened in 2007. We can plot this over time. This is sea ice going back to 1900. The record here, we have a really good record starting in about 1980 from satellites. Before that, this is mostly from ships' observations. Really good record from here. You can see this slow, steady decline. This is the extent of summer sea ice down to 2006. And then 2007, you see a 25% decrease in sea ice. So we're losing our Arctic sea ice. Well, who cares about Arctic sea ice, right? Great. Northwest Passage opens up. Fuel's going to cost less because we can ship it around the world easier. Well, we care because sea ice is essentially the air conditioner for the northern hemisphere. Sea ice is white. It reflects incoming solar radiation. Once you eliminate sea ice, you expose ocean, which is dark, which absorbs far more of the sun's radiation. And so you get caught in a vicious positive feedback loop. As you lose sea ice, the ocean warms up, it's warmer, you lose more sea ice, you lose more sea ice, more ocean gets exposed, you warm up the ocean quicker. There are now estimates that we will completely lose Arctic sea ice during the summertime, during the summer melting period, in the next 5 to 10 years. No global climate model predicted this 5 years ago, and even today, the global climate models don't get it. So the Earth's system is changing faster than our best understanding of it. While some people might say, well, hey, we don't really understand the system, let's not worry about it. What scientists are saying is we don't understand the system, so we better start worrying about it. Another sort of dramatic change in the climate system comes from Greenland. So we know that the amount of melt on the Greenland ice sheet is increasing because we have satellites that can sense the difference between dry snow and wet snow. So you see here, this is the amount of melt in 1992. Here's the amount of melt in 2002. A significant increase in the amount of melt. And what happens when that water melts on the surface, if there's enough melt, it eventually makes it down into these big holes in the ice called moules and flows to the bottom of the ice sheet. And that serves, just like the oil in your engine that allows your pistons to go up and down, that water serves to lubricate the bottom of these big glaciers that drain the Greenland ice sheet and cause them to flow faster. What we've seen in terms of the flow rate of these big outlet glaciers, I'm talking about glaciers that would flow from Mount Washington down the Merrimack Valley to Newburyport. I mean, these are many miles wide, hundreds of miles long, and they drain the Greenland ice sheet just like rivers drain the continent. And what we've seen is a doubling in the velocity of those outlet glaciers over time. This is the distance from the front of this particular Jakobshavn Glacier, which drains into Disco Island on the west side of Greenland. This is the snout. This is upstream, 50 kilometers inland. And these are the rates of movement on that glacier for different years. So you can see back in the 80s and early 90s, this glacier was moving at 6 kilometers per year, which for a glacier is really fast. At 2002, 2003, that rate of that outlet glacier has now doubled in velocity. So it's traveling twice as fast, which means it's dumping twice as much ice into Baffin Bay that eventually makes it into the Atlantic Ocean. If this behavior continues and increases, we're likely to see sea level rises on the order of 1 meter to 2 meters by the end of the century. 5 years ago, well, actually not 5 years ago now, 10 years ago, I mean, I'm a glaciologist. I'm in the glaciological community. We were all worried about the West Antarctic ice sheet. Nobody was really worried about what the stability of the Greenland ice sheet. We talked about it, but we didn't really have any measurements. This is new and shocking because we really didn't forecast this change in the Greenland ice sheet. And it's now happening, and we frankly don't know what's going to happen in the future. We do not have good models to model the Greenland ice sheet and its response to a warmer climate. We know that it's disappeared in the past. In the last interglacial period, there was very little, if any, Greenland ice sheet. But science cannot provide society with a good estimate of how the behavior of the Greenland ice sheet is going to change in the future. All right, so I want to shift a little bit. That's sort of the global picture. I just want to talk a little bit about how climate has changed across in the Northeast, which has really become a focus of my research over the past 4 or 5 years. This is one of our initial studies looking at how our winters have warmed. You can see this is the last 100 years of wintertime climate. You can see lots of year-to-year variability, but the long-term trend is one where we see over 2 degrees Fahrenheit warming over the last century, and that rate of warming actually increasing over the last 33 years. We actually looked into this in quite a bit more detail. And this is a paper that's just about to come out in the Journal of Geophysical Research, written by my graduate student. And there was, my graduate student at Days has hated me because there's this tremendous amount of data, and there's lots of gaps in it, and there's lots of problems. So we just had to figure out the best stations, and then we did a whole bunch of work to fill in the missing data by looking at what neighboring stations had. But she's done a really excellent job developing the best record of wintertime climate change across the Northeast. And then what we did is we looked at trends in wintertime indicators, and I'm going to talk mainly about temperature here, trends in wintertime temperature, and she just put a trend line over 30-year periods, starting in 1965 and going to 1994, and then starting in 1966 and going to 1966 and going to 1995, these 30-year periods, and stepping that along all the way up until we got to 1975 to 2004. So we're looking at trends, on this 30-year trends over time. And the reason this is important is because you never know where to start your record, because maybe you just start in a cold year and you end in a warm year, and so you bias the data. What she's plotted here is every one of these bars is a different station, and this is just latitude across the bottom. So here we're in northern Maine, here we're down in Pennsylvania and New Jersey. And this is the mean change in degrees Celsius per decade. So for degrees Fahrenheit, just double it. But what you see is that almost all of the stations, the trends over that time, are on the order of half a degree Celsius, a degree Fahrenheit per decade over the last 4 decades. Almost all stations in the Northeast are showing this 4-degree warming over that time period. The error bars just represent the variability in that trend by starting and ending the trend in different years. So this is a really robust result that took my graduate student 3 years to get to, that was the same as when we did the initial study. Winters are warming across the Northeast. There's no doubt about it. Just to summarize what this actually means, she also has looked at changes in snow cover days, but our mean temperature, and now I'm breaking this down by month, you can see that our temperatures, especially in the heart of winter, January and February, are getting warmer on the order of 1 to 1.2 degrees Fahrenheit per decade. So we're looking at 6 to 7 days per decade, fewer days of snow cover. In Durham, we now have 30 days less of snow cover that we did compared to 1970. We're seeing this dramatic change in our wintertime climate, and it's fundamentally linked to the fact that when you have less snow, the ground absorbs more solar radiation. So we're suffering from the same process here in the Northeast that the Arctic is suffering from with Arctic sea ice. This comes from Lake Champlain. For over 190 years, they've been tracking when the ice comes in on Lake Champlain. It was really important early on because as the northern part of Lake Champlain froze, they used it for transportation. They took their wagons and horses across the ice. So we've got this long-term record, and you can see over the course of time that the ice is coming in later and later. It's about, 2 weeks later today compared to the early 1800s. But what's really shocking about this record, if you look at the bottom, is those red dots represent years when the ice did not come in at all. There was no lake ice that formed. And you can see that of the 33 times that the lake has not frozen over the entire period of record, over 50% of those have occurred since 1970. This is not a random distribution. The system, the climate system in northern Lake Champlain has flipped now to the point where you used to have lake ice and now you don't have lake ice. And that has really important ramifications for the climate system, certainly for the ecosystem when a lake freezes or doesn't freeze, and perhaps most importantly, to the social system, right? Kids aren't going out ice fishing anymore. You can't take your snowmobiles out on the lake. And if you live up there and you get your income from people who are going fishing or snowmobiling, it's not happening anymore. I just wanted to talk about sea level rise. Global sea levels have been rising. In the Northeast, we are particularly at risk because our coast is sinking. So in response to these big glaciers that left, that were here 18,000 years ago, they left, the land lifted, but it's lifted quite a bit, but now the coast, in response to that, is subsiding. So our coast is sinking. Global sea levels are rising primarily because the ocean is warmer, it's warmed up, the surface water is less dense, it takes up more space. These rising sea levels, so we see about double the rate of sea level rise on our New England coast compared to global average sea level rise. And day to day, this isn't a huge concern, but when we have really big storms like we did a year ago in April, a year and a half ago, you can see that we have major erosion. And this is just going to continue. You know, if you own a home in Cape Cod that's close to sea level, things don't look good. So we've seen about 18 to 19 inches of relative sea level rise on the East Coast over the course of the last 150 years.
Nancy is the Director of Climate Outreach for the Union of Concerned Scientists. She keeps UCS's Sound Science Initiative tuned up and running well. SSI is a special project designed to help scientists present accurate, credible information about global warming and other issues to policymakers and to the media. A grassroots organizing veteran, Cole now works with scientists around the country to bring the voice of the scientific community to bear on critical global environmental issues.
My name is Nancy Cole from the Union of Concerned Scientists, and I'll say a little bit more about the work that Cameron and I have done together with a lot of other scientists around the Northeast. That's the focus of my work, my presentation today. So what I'm really going to do is, you've just heard a lot from Cameron about sort of the both the global picture, but also some historical information about changes here in the Northeast. What I'm going to do is zero in using information from the Northeast Climate Impacts Assessment that Cameron was one of the lead co-authors on, and talk a little bit about what global warming might mean right here in the Northeast. So we can worry a lot or not very much about what's happening up in the Arctic, but I think it really matters to know that there will be a lot of changes right here in the Northeast, and what that is going to mean to our economy, our environment, and the way of life that at least I, for one, have really come to love. So the Northeast Climate Impacts Assessment was a collaboration between about 50 independent scientists from a lot of different academic and government institutions around the Northeast and the Union of Concerned Scientists. It was the goal of this effort was really to develop and communicate a new assessment of climate change and associated impacts on key climate-sensitive sectors in the Northeast. So this study covered the area from from Pennsylvania in the south to Maine in the north, so 9 states, and several different economic sectors, including coastal areas, marine, forests, ag, winter recreation, human health, and solutions. So the bottom line here is that this research, which was released in this report released about a year ago, a little over a year ago, shows that if global warming continues to grow unabated, then the Northeast can expect dramatic changes in climate over the course of this century, with substantial impacts on key sectors and the character of the entire region. On the other hand, if the rate of heat-trapping emissions is lowered, the projections in this report show that many of the changes will be far less dramatic. They won't be zero, but they'll be far less serious. So what that basically says to us is that the emissions choices we're making today, the choices that we're making about how we get electricity in our homes and businesses, the cars that we drive, the products that we use, those choices today, both here in the Northeast and worldwide, will help determine the climate that our children and grandchildren inherit from us, and will shape the consequences for their economy, environment, and quality of life. I want to say right up front that the story I'm going to tell is a story not of what will be, but of what might be if we don't change our behaviors. Because this global warming is a human-caused problem, the good news is it's amenable to human solution. So if we've created this problem based on the choices that we've made about how we get our energy primarily from fossil fuels, then we can change that. That's the good news. So we need to both reduce our emissions, and as Cameron said earlier, we need to do it fast. And we also have to begin to prepare for the changes that we now know are unavoidable. So there is a certain amount of global warming and the associated impacts from that that can't be avoided anymore because it's going to be caused by the CO2 and other heat-trapping gases that are already up in the atmosphere. And right now, we don't have any way to get them out of there. So we're going to feel the effects of that. And the question really is, are we going to manage that smartly? Or are we going to pretend that it's not happening and face crisis after crisis? So we need to really begin to prepare for the changes that we can no longer avoid. And the good thing for us is that there are a lot of choices we can make today to reduce our emissions, and I'll touch on a couple of those at the end of my talk. There are certainly things that we can begin to do to prepare for the changes coming our way, and I'll mention a few of those over the course of my reporting on the findings. So, the first thing we know is that climate change is already changing across the Northeast. Annual temperatures are up almost 2 degrees in the past 40 years. We know that, like Cameron said, winters are warming fastest, very rapidly. Snowpack and lake ice is decreasing. Spring indicators are arriving earlier. That means things like when the trees bud, when the birds migrate, when the insects emerge. Those kinds of things are happening earlier and earlier. And extreme heat is becoming more frequent. So these are changes we're experiencing already here in the Northeast, and these changes can be attributed to the emissions that our parents and grandparents put up in the atmosphere during their lifetime. Now they didn't, it could certainly be argued that they didn't understand the consequences of their actions. I don't think that we can pretend to say that anymore. So, if we know that our emissions are continuing to increase, and like Cameron said, the most recent evidence suggests that emissions are rising at a more rapid rate than even the worst-case scenarios that scientists previously projected, then we have to say, okay, with these emissions likely to increase, what kind of change can we expect over the coming century? Now, if you're going to make assumptions, if you're going to make projections about the future, you have to make some assumptions about what that future is going to look like. And so that's exactly what the Intergovernmental Panel on Climate Change does. They have created a number of scenarios, called scenarios, that look at how much CO2 and other heat-trapping gases they expect to be in the atmosphere over the course of the century. And they look at a bunch of different things. Population growth is a big factor. The more people you have, in general, the more energy we use, the more emissions we create. You might look at energy use. You might look at economic development or types of economics. So heavy industry, a heavy industrial economy has more emissions than the service sector economy, for example. You might look at what assumptions about how technology might develop in the future and how quickly it could be spread around to the rest of the world. So obviously there's a lot of different variables there, and so the way scientists deal with that is they create a number of different scenarios that mixes those things up. So what the Northeast Climate Impacts Assessment did is it used 2 different emission scenarios to try to make some projections about the future. The first one is the one you see in the dotted red line on the screen. That's what we call the higher emissions scenario. Again, these were created by the IPCC. The higher emissions scenario assumes pretty much business as usual, continuing the emissions trends that we see today. So continuing to rely very heavily on fossil fuels for the rest of the century. If that were to happen, we would end the century at about 940 parts per million of CO2 in the atmosphere. So that's the 1,000 figure that Cameron was referring to. On the other hand, if you look at the green line at the bottom, that's the lower emissions scenario. That scenario assumes that we begin to see some shifts in technology, a less carbon-intensive energy future, and that one ends the century at 550 parts per million. Those are the two scenarios that were used in this study, and the idea that the scientists had was that they're sort of bookends. You know, if you could kind of look at both a higher emission scenario and a lower one, and if there were differences between them, then it would show what difference it would make if we do something to reduce our emissions. And as you'll see during the rest of my presentation, there are a number of situations where it makes a tremendous difference, whether we are on the higher emissions pathway or the lower. But the one thing I do want to point out here is you heard Cameron say that many scientists think that 450 parts per million in the atmosphere is the highest we should go without a significant risk of significant problems. In fact, some very prominent scientists are suggesting we need to stay at 350. So already the findings in this report are going to be are sort of higher than what we would see as the optimal amount of emissions we want to have in the atmosphere. So a few times throughout the presentation I'm going to say, remind you again that what we really need to do is get lower than this lower emissions scenario. This should not be a floor for us. We need to aim to be lower than that. This first graph shows you the Northeast average annual temperatures. So what I mean by that is annual average means you're averaging day and night, you're averaging summer and winter, you're averaging from Maine to Pennsylvania. Okay, it's a composite sort of gross level picture. Horizontal axis you have years from 1900 to 2100, and on the vertical axis you have temperature change in degrees Fahrenheit. The yellow line represents the lower emissions scenario results, and the sort of red line represents the higher emissions scenario results, and the black line here at the beginning represents observations. That's what's actually happened. What you can see is by the end of the century, if we don't do anything to get our emissions under control, we are very likely to see annual average temperatures over the Northeast region increase by up to 12 degrees Fahrenheit. Now, just to put that in perspective, at the height of the last ice age, for example, many scientists believe the difference in temperature was around 9 or 10 degrees Fahrenheit. So we are talking about, a huge change in temperature. On the other hand, under a lower emissions pathway, we can keep that temperature increase to less than half of the higher emissions scenario. So already you can see a pretty tremendous difference between higher and lower. Now, this is a place where you might say, well, maybe we really don't want to go to 6 degrees higher annual average temperature, and that would be a real reason why we need to keep our emissions lower than even the lower emissions scenario used in this study. You notice that the two emission scenarios don't really diverge until about 2040, 2050, mid-century. So that's the clearest picture I can show you of what difference it will make whether we reduce our emissions or not. We're setting the pathway today. There's a certain period of time between now and 2040, mid-century or so, where the two scenarios track together. And what that picture shows us is warming that's already unavoidable. Heat index, how it actually feels to us. So even though the temperatures are projected to get high, humidity or heat index is going to get higher. So if you look at that map, hopefully you recognize the state of Massachusetts. The gray is the historic heat index for the state, which is what it's felt like for the past 30 or so years. Using the same color scheme, the yellow is the lower emission scenario, the red is the higher. What this graphic shows you is that, again, if we stay on a very fossil fuel intensive pathway, and continue to emit a lot of heat-trapping gases, we could expect that by the end of the century, summers in Massachusetts will feel more like South Carolina. I'm not talking about winter, when it might feel nice to take a little break. I'm talking about July and August in New England, feeling like July and August now feels in South Carolina. On the other hand, here's the good news, we can keep these changes so that it feels much more like, say, Maryland or Northern Virginia than South Carolina. That's a significant difference. This is a graphic that will show you for Vermont, for New Hampshire, and for Maine. So for those of you from New Hampshire, by the end of the century, under higher emission scenarios, summers are much more likely to feel like North Carolina than like the beautiful summers you usually experience. One of the things that this study looked at very carefully is the potential for extreme heat in the big cities of the Northeast. Obviously, there are millions and millions, tens of millions of people who live in the big cities along the eastern seaboard. Big cities are even more susceptible to extreme temperature because of the heat island effect. And so there's a great cause for concern about extreme heat in the big cities. And so if you look on this graph, again, along the horizontal axis, you've got time. On the vertical axis, you've got days per year over 90 degrees. And the gray box on the far left, that again is your historic reference period. So in the past, it used to be that Boston would experience fewer than 10 days over the course of a summer over 90 degrees. By the end of the century, under the higher emissions pathway, taking no action to reduce our emissions, we are looking at more than 60 days every summer over 90 degrees in Boston. Under the lower emissions pathway, you can see again a tremendous difference. That extreme heat is cut in half. And if you look at the days over 100, which are extremely rare in Boston, by the end of the century, we could see 24 days over 100 degrees. Substantially less, only a quarter of that, if we do something about reducing our emissions and keeping them along the lower emissions pathway. The same kind of thing, say, in Concord and Manchester, in Buffalo, cities farther north that have traditionally been very cool are likely to see pretty extreme changes in extreme heat. Poor air quality, or bad air days, is caused by a combination of pollution and temperature. Increasing heat is going to mean increasing bad air days. So we're talking about some pretty significant heat problems here, health problems here. Not only increases in heat stress, heat stroke, heart attacks, the kind of things that the human body has a difficult time adjusting to extreme heat, but we're also talking about respiratory problems when you combine sort of heat and pollution. So we're looking at some very serious threats to human health. With more CO2 in the atmosphere and a longer growing season and higher temperatures, guess which kind of plants really, really love that kind of an environment? It's particularly weeds and allergen-producing plants. So there's a lot of evidence that's now suggesting that not only do the plants grow better, but they also produce more pollen. So for those of us who are allergy sufferers, this picture is also a sad one. Likely to be changes in precipitation, particularly how the rain and snow is delivered. We're likely to see increasing winter precipitation, but it will come more in the form as rain than as snow because as the temperatures go up. And we're likely to see more frequent and intense periods of heavy rain. And we've experienced a number of those kind of extreme rain precipitation, particularly rain events, over the past several summers, as exhibited by this picture here in New Hampshire. Cameron's also talked a little bit about sea level rise. I need to talk about impacts to coastal areas, which of course is a fundamental part of the Northeast. There are likely to be more frequent flooding, like that picture at the bottom, which was taken, I think, in Revere or Chelsea. More coastal erosion. The top right picture is taken from the New Jersey coastline. And also wetland inundation and expected loss. So there'll be some significant changes along the coastline in a lot of different ways. As sea level is increasing and storm surge is getting larger, the barrier islands, those sort of islands off the coast that provide a lot of protection both for wetlands and for homes, on the other side of the barrier island, they're at increasing risk. This is a breakthrough of the barrier island in front of Chatham that happened from the big nor'easter in April of 2007. Boston, New York, Atlantic City, all of those cities are right on the coast. Federal Emergency Management Agency, or FEMA, develops a system called the 100-year flood, which is just a term that they use to help city planners prepare infrastructure changes so that they can kind of understand, what might a kind of worst-case scenario be if there were storm surge and flooding in Boston and the other big cities. So what this graphic shows you is Boston, this is Back Bay, so some of the big landmark areas in downtown Boston, Commonwealth Avenue, Newbury Street, Copley T, the Esplanade, the John Hancock Tower, that sort of area of Boston, and what it might look like as sea levels rise and storm surges increase. So what you see in the hatched area, the sort of dark blue lines, right now that is the 100-year flood zone. But as, of course, sea level rise, the 100-year flood zones are going to rise. So what you see with the projected 100-year flood zone in 2100 is very frequent flooding of very substantial parts of what is now Boston. The sea level rise projections that were used in this report were based on the most recent IPCC report, and at that time the IPCC did not include projections about projected changes in Greenland melting, because I don't know why they didn't do it. The science.
Too much uncertainty.
Too much uncertainty, so they didn't make any projections. But over the past couple of years, that science has progressed, and like Cameron indicated earlier, there's now a lot of evidence suggesting that sea level rise will be substantially higher than the IPCC projected. And so using those new sea level rise projections, what we might expect is that what I described as a possible 100-year flood in 2100 will actually be high tide in 2100. It's extremely unlikely that this is going to happen. I mean, Boston will and Massachusetts will take pains to protect the city as best as it can, and there's a lot of engineering solutions and other things that can be done to help protect this incredibly valuable part of the Boston landscape. But I just ask you to think about, if this part of Boston is seeing high tides that look like this, what kinds of investments will have to be made by the state of Massachusetts, by the city of Boston, by the people of the U.S. to protect Boston from this kind of damage? So when anybody says to you, oh, it's going to be expensive to reduce our emissions and to change our energy system, I want you to think about how expensive this is going to be, and what this is going to look like in New York City, which is almost as bad, and what this is going to look like all up and down the coastline of the East Coast. So there are tremendous costs associated with not doing anything to reduce our emissions. And we don't talk about that very much. But I think that's a really important part of this discussion now, is what kinds of expenses we're talking about to protect ourselves from a changing climate, and what will happen if we don't. We are expecting to see substantially more drought conditions. So you've got this really terrible thing setting up of sort of more frequent and more rain in the spring and in the fall, with longer dry spells right when you need it in the growing season. There will certainly, all these changes in temperature and precipitation are certainly going to mean impacts on agriculture. So climate change will bring some new opportunities. More CO2, longer growing season might in fact mean that some crops that can't currently be grown in the Northeast could in fact be grown in the Northeast. But there's a whole new set of risks and costs that also go along with this. Weeds and pests that have currently been limited, have not moved into the Northeast because it's been too cold here, are now finding their way farther and farther north. Extreme rain at the time that we don't want it. A more variable climate, which makes it hard for perennial crop farmers, for example, to be able to make it through the seasons. And of course, additional costs like irrigation in areas that used to be rain-fed agriculture. One of the interesting things, I think, for Massachusetts is to consider that many of our very lucrative specialty crops require cold winters. So all these things you didn't value about winter before, hopefully you will now. But a lot of like apples and grapes and cranberries require a certain chilling requirement in the winter in order to flower and fruit in the summer. And by the end of the century, by mid-century, it seems that in the two highest cranberry producing areas of the Northeast, the chilling requirements are likely to be unmet a substantial amount of the time. So it turns out that New Jersey, which is that sort of brown spot on the bottom, and of course southern Massachusetts are the two big cranberry growing areas in the Northeast. And by even as early as mid-century, less than 80% of the years under the higher admission scenario will be cold enough in the winter to support cranberry growth in Massachusetts. Can you imagine Massachusetts without cranberries? I think about forests a lot as I look out of this beautiful window and on my drive up here. So under current conditions, which is the map you see there, you can see that much of the, well, Maine is dominated in large part by the very deep spruce forests of the northern woods, and that much of Massachusetts and New York and Vermont and New Hampshire are, you know, the hardwoods, the maples and the beeches and the birches that give us our beautiful fall color. Lower emissions scenario, you can see that certainly much of that environment will be missing out of Massachusetts, but a lot will be left in Vermont, New Hampshire, and western Massachusetts. But under the higher emissions scenario, we lose very, very much of the suitable conditions for the types of trees that we love. And the same thing with winter recreation. You heard Cameron say how fast winters are changing. What this graphic simply shows us is in the historic period, the amount of the Northeast that we could expect at least an inch of snow for at least 30 days over the course of the winters. You can see it's most of the region, but by the end of the century, under the higher emissions scenario, there's basically snow left in very few parts of the region. What I said at the beginning was that I want to emphasize again, this is the story that I've just told, is the story not of what will be, but of what might be. And whether it's what actually happens is up to us. It is very literally, the future is in our hands right now. So we need to reduce our emissions.
As Tony Blair states, the blunt truth about the politics of climate change is that no country will want to sacrifice its economy in order to meet this challenge. But all economies know that the only sensible long-term way of developing is to do it on a sustainable basis. Thank you for joining us today. We hope you have been influenced by what we presented to you today.